What if the key to unlocking the next generation of artificial intelligence isn't found in feeding models more data, but in teaching them the fundamental rules of the universe they inhabit? We often assume that brute force and massive datasets are the only path forward, but a quiet revolution is happening right now, proving that structure, logic, and foresight might just be the missing pieces we've been looking for. Welcome to a journey through the creative frontier of modern science, where we explore how new research is reshaping the way machines learn, see, and understand our world. Today, we are diving deep into 3 groundbreaking studies that challenge the status quo of artificial intelligence. You will discover how looking into the future can clarify the present, how ancient mathematics is solving modern medical mysteries, and how dynamic adaptability is fixing the glitched visuals of our digital age. Stay until the end because these findings don't just improve algorithms. They fundamentally alter how we approach complex problems in medicine, media, and beyond. For decades, the dominant narrative in artificial intelligence has been that more data equals better performance. We have built massive black box models that ingest terabytes of information, hoping that patterns will simply emerge from the chaos. However, this approach often leads to systems that are powerful yet brittle, capable of recognizing a face but unable to understand the emotion behind it, or predicting a heartbeat but failing to grasp the rhythm of life. The core problem is a lack of structural integrity. When models rely solely on raw data without incorporating the underlying laws of physics, time, or semantics, they struggle with ambiguity, drift over long periods, and interfere with their own logic. This limitation holds back critical applications, from monitoring the health of millions to generating the complex visual stories that fill our screens. We have been building engines that are fast but directionless, and the cost of this is measured in missed diagnoses, inconsistent predictions, and visual artifacts that break the immersion of our digital experiences. But what if we change the rules? Imagine a teacher who doesn't just correct your mistakes after you make them, but somehow guides your hand before you even lift the pen. This is the essence of a new framework called Video-Mirai. Researchers have discovered that by using future frames of a video to supervise the current state of a model, they can instill a sense of causality that was previously missing. It is like giving the algorithm a glimpse of the destination before the journey begins, allowing it to navigate the present with unprecedented clarity. In recent tests, this approach boosted performance scores from 83.8 to an impressive 84.6, proving that a little foresight goes a long way. Now, take this concept of structural rigor and apply it to the human heart. Our hearts beat in a rhythmic cycle, a pattern that repeats tirelessly throughout our lives. Traditional AI models, when tasked with modeling this motion over decades, often suffer from drift, where small errors accumulate until the prediction no longer matches reality. It is like a clock that slowly loses time, second by second, until it is completely out of sync. Enter 4D fMesh LDM, a revolutionary approach that applies a truncated Fourier series to cardiac data. By enforcing strict mathematical periodicity, this method guarantees that the model remains in perfect sync with the biological rhythm, eliminating the drift entirely. Tested on 5,000 subjects from the UK Biobank, this technique demonstrated near-zero error, ensuring that long-term predictions remain physically plausible and mathematically consistent. This is not just an improvement in accuracy. It is a guarantee of reliability for personalized medicine. Finally, consider the challenge of creativity itself. When we ask AI to generate images from complex, multi-layered text, a phenomenon known as concept bleeding often occurs. Features from one idea bleed into another, creating visual interference that degrades the quality of the final image. It is similar to trying to paint a landscape while someone else keeps splashing different colors onto your canvas. The solution lies in W-switch and W-composite, frameworks that dynamically adjust the weights of learning modules based on the semantic density of the prompt. Instead of a static setting, the model adapts in real time, prioritizing relevant concepts and suppressing noise. This dynamic weighting acts like a smart filter, ensuring that the generated visuals remain crisp, coherent, and true to the original narrative. Know how complex the story becomes. These discoveries collectively signal a profound shift in the trajectory of computational science. We are moving away from the era of pure, end-to-end black box modeling, where data volume was the only metric that mattered. Instead, we are entering an age of hybrid supervision, where domain-specific constraints are woven directly into the fabric of learning objectives. This evolution matters deeply for researchers and engineers alike. For those studying population health, the ability to enforce cycle consistency means we can now conduct large-scale, long-term studies with confidence, reducing the risk of spurious correlations that could lead to incorrect medical conclusions. For creators and industries reliant on rapid content production, dynamic weighting offers a scalable solution to generate high-fidelity assets without the need for constant manual intervention. Furthermore, the integration of future frame supervision suggests a new paradigm for real-time control systems, potentially revolutionizing fields like autonomous vehicle navigation and climate modeling, where understanding cause and effect is critical. However, this exciting progress also brings new questions to the surface. While specific studies like Video-Mirai show